Hi, good afternoon. My name is Jade Vinson. I'm with one of the sponsors, Talking Leaves, and was one of the organizers of the conference last year. It's my pleasure to chair the afternoon session. And first in our lineup, it's my pleasure to introduce Ziping Xin from NC State.
Okay, good afternoon. Thanks for the introduction. Well, 1 year ago, when Charles Leston, who is a distinguished professor at MIT, visited Duke, I talked with him. So one sentence from him actually gave me very different views at software computing. Which is performance, or in other words, speed is the currency of computing. What does that mean? Now here, the speed is how fast your programs can run. With performance, with good speed, you can buy accuracy for machine learning tasks, for example, because then you can take more time to search, find the better models, and in a given amount of time. And then for inference, you can have more complicated models deployed, and you can get a higher accuracy. And similarly, you can, with great performance, you can also do lots of things to improve the reliability of your computing, or security, putting security measures into the computing. And you can do lots of other things. During runtime, you will have that amount of time left after improving the performance. So this is the fundamental motivation for our group's research, which is performance-centric. Now, our research has been focusing on these three areas. One area is machine learning, AI, and data analytics. The other is heterogeneous computing, which is related to accelerators, GPU, neural network accelerators. And then the other is the foundations of program languages, program systems like compilers. These are system software that are critical for improving software efficiency. And the recent research topics from our group includes real-time machine learning, high-performance machine learning, accelerators, emerging type of memories like non-volatile memory, and auto programming, and code optimization in general. Now, today's topic is about machine learning, so I'm going to focus on two pieces of work from our group recently conducted. These two pieces of work are both trying to improve the speed of machine learning. So speed of machine learning is critical. For training, we know that, well, training is very time-consuming for large models. You take days, sometimes some weeks, to just finish training the one model. And then for inference, it's also very important, especially think about in real-time systems like driverless cars. You don't want the car to take several minutes to really stop after seeing an obstacle. So the prior work on expediting DNN mostly focused on DNN itself, which is the weights of the parameters in the deep neural networks. And they try to reduce the number of weights, or quantize the weights, or leverage sparsity in the network to improve the speed. Now, our focus in this work is about inputs. The inputs can be the inputs to the whole neural network, can also be just inputs to each layer of the neural network. Now, this is technique, we call it deep reuse. Now, deep reuse, it's a very appealing technique from our perspective, because it can improve both training and inference significantly in speed. It does not cause any accuracy loss. Same time, it's easy to adopt. You don't need to retrain your model to use this technique. You only need to replace the operator in your TensorFlow, for example. And then it can also help both GPU servers and as well as edge devices or smartphone. Now, after we published the deep reuse work, it has drawn lots of media attentions. The news got released in many channels, in many different languages. Now, I'm going to use this slide to convey the intuition. The intuition actually of deep reuse is pretty easy to get. Now, look at this picture. Now, this picture has many pieces. They are very similar. Now, this kind of similarity is a fundamental property for deep reuse to leverage. Such similarities also exist across images. If you look at some pictures on this slide, you can see some grasses, lawns in different pictures look very similar, and so on. Moreover, such kind of similarities also exist on the intermediate level, or the activation maps we call in neural networks. And these similarities leveraged by our technique to improve the speed of neural network. Now, before getting into this technique, I want to introduce a term which is called neuron vector. Neuron vector, if you look at this slide, it shows we have we have many layers in here, and each layer have many neurons. Now, a consecutive 4 neurons, their value together form a neuron vector. So this is our term. Now, certainly that does not have to be 4, could be longer than that or shorter than that. And here is the basics on convolution. Now, convolution is essentially matrix multiplication. Now, we have this image. We want to do convolution on the filters. Now, one way to do it is we first unfold the image into a matrix. And this unfolding is to take one tile of the image that you want to do convolution, put all of the elements into one row in the matrix. And then you do this for every tile. You get this X matrix. And then the convolution becomes X matrix multiplied with the weight matrix W. All right, so these are the basics about the convolution. After we understand this, we can see how deep reuse works for neural network. So let's look at forward propagation. Now, forward propagation, the core computation is convolution in CNN. And that is just this kind of matrix multiplication. Now, suppose that we take half of the row as one neuron vector, then this matrix X has 8 neuron vectors. This multiplication would involve many dot products between these vectors and the vectors in the weight matrix. Now, if we want to use deep reuse, the first step we do is we want to find those similar neuron vectors in each column of vectors. And that is called the clustering. Now, we want to do clustering in this example. Suppose that we use different colors, use the same color to represent neurons that are very similar to each other. And then after clustering, we get the centroids. The centroids are represented on the slide, and we have only 4 centroids here. And then the original multiplication becomes the centroid multiplied with the weight vectors. And that will take much fewer dot products to produce. Now, after producing these results, then we can reconstruct the original output by duplicating these values and add them up. So this is the third step, reconstructing step. Now, when I talk about the second step, I want to come back here to emphasize this term, remaining ratio, which is a metric we use. And it is the size of the centroid matrix divided by the size of the original matrix X. So the smaller it is, means we can save more computations. All right, so that is how deep reuse could work for forward propagation. Now, we can see that, well, we save some computations by using centroid matrix to do the computation, but we introduce first and the last step. These are extra work, clustering, reconstruction. So for deep reuse to be effective, we have to make those 2 steps as fast as possible. And that is the kind of design pretty tricky part about this technique. Now, the first step, how to do clustering, find the similar neurons. Now, what we use is LSH clustering. LSH stands for locality sensitive hashing. And the basic idea is easy to understand. Suppose we have these X, 4 vectors, X matrix here. And then if we want to use LSH, we first need to define several hashing vectors. They are the 2 vectors V1 and V2. Now, when we want to do clustering for these 4 vectors, we just take each X vector and then multiply it with these 2 hashing vectors V1 and V2. Then we would get the values multiplication dot products. Use the dot products to compare with 0. And then we would get either 1 or 0 as the output. That is a bit vector. We call it a bit vector. So each X would produce 1 bit vector. And then if 2 X's vectors produce the same bit vector, they are considered to be in the same cluster. Now, this technique is clustering is very attractive for our usage because one, it's very fast. Second, it does clustering in a continuous manner. We do not need to collect all of vectors and then do the clustering, which is very slow and not very friendly for these deep reuse to use. Now, next is, if we want to use deep reuse in the best way, we need to consider a number of factors. Now, we talk about clustering methods, LSH. We also explored some other methods like k-means, hypercube, and we also need to study scopes of clustering. We mentioned that similarity could exist within an image, but also could cross images. And then we have these 3 scopes studied: single input level, single batch level, or cross batch. And then clustering granularity, which is how long the neuron vector could be. And then the last is similarity matrix. This is used only for k-means and hypercube, angular cosine distance or Euclidean distance. Now here, this slide would let's start looking at the experimental results. So this slide gives you the kind of data sets and neural networks we used in our experiments. These 3 neural networks actually are pretty popular, publicly available. And we compared the results on two devices. One is on server, which has GPU. The other is on smartphone from Huawei. Now, here, this slide shows the results that, some such kind of similarity we talked about earlier do exist. Now, here, this is for AlexNet. What it shows is on the 3rd convolution layer. Now, exercise shows the remaining ratio. Recall remaining ratio is the size of the centroid matrix divided by the size of the original matrix. So smaller means better. We can save more computations. And the y-side shows the accuracy of the network, entire network. Now, the default network accuracy is just as what the top lines show. And what these 2 curves shows that, well, if we do single input level deep reuse or single batch level deep reuse, what is the changes of the accuracy when we use different number of clusters, so that it affects the remaining ratio. So what it shows is, well, the orange curve shows 15% of data computation is enough to produce the same accuracy as the original network does. So this is encouraging because that means we could potentially have 7 times speedups by using deep reuse without losing accuracy. And this graph shows the speedups of these 3 networks, the distribution of speedups, because we have many batches. This is per batch time. So what it shows here is baseline, which is default network, and the deep reuse, which is our approach. Now, across all 3 networks, we get significant speedups here. And these 2 tables show the results on server and our smartphone. The accuracy column shows the original network's accuracy. Delta ACC is the changes after using deep reuse. Now you can see that the delta ACC is almost 0. So that means we do not have noticeable changes in accuracy. And S is the speed up column. So we have up to 2 times speed ups for inference. Now the other 2 columns shows the overhead of our first and third step, the clustering and reconstruction. Now you can see that the speed up, the overhead is pretty significant. It is because our deep reuse already reduced the time a lot. So in the remaining time, the speed up becomes significant. Now recall that in the previous slide, we showed that potentially we could have 7 times speed ups on AlexNet. But here we have only 2 times. This is fundamentally because those overhead. So all of the overhead are counted into this timing. On smartphone, we have also significant speedups, even more speedups on the server. And furthermore, this technique actually can be used together with some existing optimizations like network compression. We talked about the previous work have been trying to improve the efficiency by you reduce number of weights doing compression. Now, if we first do compression of the network, and then we get a new baseline, and we measure the time, and then apply our deep reuse above that, then we can get extra speedups here, actually even more speedups here compared to the time of the compressed network. So this indicates this technique can be complementary to existing optimizations. Now, besides inference, this technique can also be applied to saving training time significantly. Now, we know that forward propagation definitely also exists in training, but training also have backward propagation. Now, in our paper published at SADE this year, you can see the proof. If we consider backward propagation, we do not need to do reclustering. Only one time forward, during forward time do clustering. The clustering results can be safely reused for the backward propagation. And furthermore, for training, we can also be adaptive. We can do very aggressive reuse using very few clusters at the beginning of the training, but then gradually reduce the aggressiveness, and it can converge to the original accuracy. Now, using this for saving, we can save up to 69% of training time. Now, here is a short summary about this deep reuse part of my talk. Now, our study shows that tremendous similarities do exist in real machine learning tasks and neural networks. And leveraging these can give us large speed up for both inference and training. And the clustering methods LSH is very effective in this context. Now, one thing I want to mention is we looked at the results. LSH clustering takes lots of time. We have some undergoing work, use FPGA, which is an accelerator, to remove that overhead. The preliminary results are very promising. Now, in the rest of my talk, I'm going to quickly go through another piece of work we published at this year PLDI, which is the top conference in programming language area. It is about CNN pruning using compiler frameworks to do that. Now, CNN pruning is such a task. Now, if we want to build up a predictor for example, predicting the species of different dogs, and we can start with a general CNN model existing, like GoogleNet, which is large for general image recognition. It may not work very well for this specific task, but what we can do is we can prune this large network and then retrain it on some dog datasets. And this can produce a much smaller but more accurate model for this specific task. So this is a common practice in building up neural networks in industry, which is called CNN pruning. Now then we can deploy it on some small devices. Now the problem with this is it is very time consuming. Now think about this, if we have 50 layers of convolution, and each layer, suppose we only consider 2 possibilities of pruning 30% or 60% top, the least important filters. Then we would have the whole space of the network configuration would be 2 to the power of 50. And suppose that one batch 64 images would take, um, 0.085 seconds, and then 100 of these CNNs, the training, we have to retrain them. Retrain would take 4 days, and let alone this large number of configurations. So the goal of our work, this piece of work, is try to largely reduce this time, but without sacrificing the quality of the pruning. Now, the basic idea is composability. Now, the composability comes from such an intuition. Now, if you look at these two networks, these two can be two variants of the original large network that we need to investigate. Now, in the parentheses, it shows the pruning rate of the layer. Now, what we can see is that these two networks are not completely different. They actually have lots of common layers. And then these common layers may be able to, well, if we train these layers, the result may be usable across these different networks. So this is a composability intuition. Now, there's some key questions. One question is, what does such kind of composability really exist for CNN pruning? In other words, if we do the training of each pieces of the network and then put them together, will that really be helpful? Now, second question is, if the first question is positive, how can we effectively translate this composability into speedups? Now, for the first question, we did a systematic study empirically and empirically proved why this kind of composability largely exists. Now, for the second question, we developed such a compiler-based framework called WOODS, which is drawn here. I mean, I'm not planning to go through this framework in detail. Now, what I want to tell you is this is a framework that it can really do this pruning based on all of the training and acceleration automatically. And we have a compiler to automatically do all of the code generation transformation to do that. Now, one interesting part I want to mention, explaining this talk, is about the first box on the left-hand side, hierarchical tuning block identifier. This actually is a very important, also interesting part, because think about if you have hundreds of networks you want to train, how do you define the building block, each tuning block, such that you can tune them and you want to maximize the reuse benefits of these pre-tuned blocks. Same time, you want to minimize the pre-training overhead. So this is the goal of this block. And what we do, the way we do it is through hierarchical compression. So there is such an algorithm called a sequitur, which can do the compression of a sequence and then produce a context-free grammar, which is also a direct acyclic graph. And based on that, then we can identify the best set of building blocks. Now, here is a small example. Suppose we have 4 neural networks, and then each one has certain kind of pruning rate. And then we would represent each one using a sequence of notations, numerical notations with pruning rate in the parentheses. And then put them together with certain kind of ending marks in the middle, become a sequence of strings. Now we can apply this hierarchical compression algorithm on the string, which can produce such a context-free grammar. You can ignore it if you don't understand the CFG, but it is equivalent to such a DAG. And on the DAG, directed acyclic graph, it will be much easier to figure out what is the best set of building blocks. Now, here is some results on this. Now, composability do exist through our study on several commonly used networks and many, many images. And then we also showed that hierarchical compression is useful. And the WOOS compiler can make the adoption of this technique very easy to do. And finally, speedups is up to 186 times speedups for pruning. So the whole pruning process can be shortened from 1 day to less than to several minutes in this case. So the graphs here, what it shows is on 2 neural networks, the orange curve are those that after pruning, after pre-tune of the building blocks. And then the network can start with much higher accuracy and converge to a higher accuracy in a much shorter period of time compared to the blue curve. Blue curve is the original. So with that, I think I finished both pieces of work. And at the end, I want to mention quickly mention three other work. If you're interested, you can check our papers. One is we also develop a framework with Oak Ridge National Lab, and which can automatically do efficient ensemble training. So if you want to train many DNA instances at the same time on the cluster, this framework could be very useful. And the next one is we have also a technique called TEDOC, published at VLDB and ICS. This technique is very interesting. We were very excited about it because it is the first technique that can do data analytics directly on compressed data without a decompression. And that means it can save 10 times the space, memory, and also it can speed up the whole analytics by several times. All right, with that, thanks for your attention.
So in your adaptive reuse work, what's the trade-off with memory as you're doing all these extra calculations and memory access from highly regular data to this less regular data?
Good question. So this actually is not, after deep reuse, the access is still regular because we get the centroid matrix. So it's still a dense matrix, it's not sparse. And then on the dense matrix, you can reuse the GM, like the library, multiplication library, from the hardware producers. And there's no irregular memory access except you want to, no, I don't think so. Even in reconstruction time, it's still pretty regular finding out where you put the data and reconstruct the matrix. There's no irregular. But you mentioned the space. Space actually is an interesting aspect because when we use deep reuse, we actually could use a little bit more space. We need to save some previous computational results. And there is one work we are doing, which is we actually do not have to reconstruct the final matrix. We can directly use the centroid computing result to do the next layer computation potentially. So that if we can skip reconstruction, we can even save space. Good question. So the question is it possible to apply deep reuse to other types of neural networks, like transformer? So the answer is positive, because the reason I say it's positive is because deep reuse essentially what it does is if you have a computation which does a repeated matrix multiplication, and with some weights or some metrics do not change, then there's potential to use it. That's the pattern. So right now we haven't experimented with transformer. I want to say, but what we are working on right now is on other network like LSTM, like ResNet is another kind of type of CNN, and we have seen very positive results at this point.